Welcome to the nature of chemical energy. Alright, so thermodynamics is the study of energy and its interconversions. Now, energy is the capacity to do work or produce heat. Now, you've already heard something about energy, you know some general things about it, and you've probably already heard of the law of conservation of energy, which states that the energy can be converted from one form to another, but it can't be created or destroyed. So the sum total of energy in the universe is constant. We can just move energy from one place or one object to another, or from one type within an object to another. So we have two main types of energy. We have potential energy and kinetic energy. Potential energy is the energy that matter possesses due to its position or its composition. So this may be something like potential energy due to position, which may be position within a gravity field, so like a weight raised above the ground, above the surface of the Earth. So it's in Earth's gravity field, it's being attracted towards the center of the Earth, and its position relative to the Earth influences how much potential energy it has. So the potential energy, the EP here, is equal to mgh, where EP is the potential energy, m is the mass of the object, g is the acceleration due to gravity on Earth's surface. This is 9.8 meters per second squared, and h is the height above the surface, or the height that the object can fall. So wherever it will land and stop moving, that's the height up from there against that gravity field. That's the height that we're talking about. So potential energy due to position may also be due to position within an electric field. So this is something like an electron near a proton, near the nucleus. That electron and the proton are attracted towards one another. Each of them has a potential energy. The electron has a potential energy because it's being pulled towards the proton, just like an object is being pulled towards the center of the Earth. Likewise, the proton has some potential energy because it's being pulled towards the electron. Incidentally, the Earth, when you have an object near the Earth that's being attracted towards the Earth also has some potential energy because it's being attracted towards that other object. It's just that the Earth is so massive compared to most objects that we think about that we can largely ignore. That potential energy is so small distributed amongst the mass of Earth. Potential energy could also be due to position within a magnetic field. So this is like an electron near an electric current. If we have an electric current, that creates a magnetic field. And if we have something that's magnetic, an electron is magnetic, near that magnetic field, it acts the same as it'll either be attracted to or repelled, just like an electron and a proton with each other. There are other forms of potential energy as well. I don't want to get into those. So potential energy due to composition may be due to energy stored within matter. So this energy may be released during a chemical reaction in the formation of chemical bonds. So when we form bonds, we release energy. When we break bonds, we have to put in energy to get those bonds to break. So the energy could also be stored as matter itself. Einstein's famous equation E equals mc squared. The m there is the mass of some object. C is the speed of light. When we square it, that's how much energy that object has just sitting still. That's how much energy is wrapped up in that mass. So the more massive something is, the more energy it has. So that was potential energy. We also have kinetic energy. Kinetic energy is the energy that matter possesses due to motion of some kind. So in general, kinetic energy, EK here, is equal to 1/2 mv squared, where m is the mass of the object and v is the velocity. But note here that in this case, by velocity, we really mean speed, because velocity is both the speed and direction. So velocity is a vector. Here we really mean the speed of the object, because it doesn't really matter which direction the object is moving in. And also note that the velocity could be a negative number, but speed has to be a positive number. Note that by squaring the velocity, it doesn't matter whether we have a negative in there or not. The negative sign goes away. Alright, so now let's talk about heat and temperature. So temperature is a measure of the average amount of kinetic energy that the molecules in some object have. And so This is different than heat, because heat is a measure of the amount of energy transferred from one object to another, or from one system to another. So, note here that an object can't have heat. An object doesn't have heat. This board doesn't have any heat. My body doesn't have any heat. My body may be losing heat to the air around me. The board may be losing heat to the air around it. But in order to have any heat, there has to be a transfer of energy as heat from one object to another. So heat really is the transfer of energy as random motion, because this kinetic energy that's in the molecules, we're not talking about ordered motion like if we take an object and we throw it. All of the molecules are moving in the same direction, or at least they all gain that same amount of kinetic energy. But random motion, where the molecules are moving in different directions, that's the heat that we're talking about here. And so some object doesn't have any heat. It's transferring energy as heat. That amount of energy that gets transferred, we call that heat, but one object doesn't gain any heat and another lose heat. It's gaining or losing energy as heat. So there's a difference between heat and temperature. An object has a temperature, and the temperature is a measure of how much of that random kinetic energy the molecules have. And it's an average. So each molecule in the object has a different amount of kinetic energy. Some of them are moving faster, some of the molecules are moving slower, but there's some average to that distribution, and that's the temperature that we talk about. So, heat is different than work. Work is also a transfer of energy, but work is an amount of energy used to apply a force to an object that has moved some distance. So, in order to do work, we have to move some object some distance against some force. So we say W equals Fd, work is equal to force times distance. So the force here is the force that's being opposed. If I take, say, a ball and I throw it parallel to the ground, I'm not opposing the force of gravity, because I'm throwing perpendicular to the force of gravity. If I take a ball and I throw it up, now I'm opposing that force due to gravity. And so now I've done some work. But if I throw the ball sideways, I haven't done any work. Likewise, if gravity pulls the ball down towards the ground, gravity isn't doing any work either, because it's not opposing any force. Or, let's say I take a ball and I set it on a table. The table isn't doing any work, because even though the table is applying a force opposite the force due to gravity, gravity is pulling the ball down, the table is pushing the ball up to keep the ball from moving anywhere, the distance that the ball moves is zero. So the table hasn't done any work either. So you have to have a force being opposed and a distance moved against that force. So, again, there are two ways to transfer energy. One is through heat, and the other way is through work. So, both of these things, work and heat, are things that an object can't have. I can't give work to an object, but I can transfer energy as work to the object, or as heat to the object, or the object could transfer heat or work, transfer energy to me as either heat or work. But once that energy is obtained by the other object, either by me or the object, we don't have heat or work. We haven't gained or lost heat or work. We've gained energy as heat or as work. So these two, heat and work, depend on the pathway, the way that we get from one place to another. So the pathway is the specific conditions that determine the way that energy is transferred from one object to another. So heat and work are pathway dependent. That is, they are path functions. They depend on how we get from one place to another. This is as opposed to, say, state functions, which only depend on the initial and final state. It doesn't matter how we get from here to there. So the total amount of energy transferred is a state function. It doesn't matter how we transfer that energy from here to there. The total amount of energy is the same. But we could transfer that energy as heat, or we could transfer it as work, which is why these two depend on the path. They depend on how we transfer that energy. I could transfer all of it as work. I could transfer all of it as heat. I could transfer half and half, or any fraction thereof. And so these guys depend on the path that we take, how much of the energy is being transferred in each way. But the total amount of energy transferred doesn't depend. It only depends on the starting and ending point of our system. So this is a state function. A state function is a property of a system that depends only on the current state of the system. The current state, so the initial state and the final state. It doesn't matter what we did in between. So state functions don't depend on the path taken between these two states, only upon the initial and final states. So heat and work are path functions, something like total amount of energy, internal energy, that is a state function. So let's look at some more real-world examples maybe. So if we have some point, we start out here and we end up over there. The displacement that we take, or the displacement that we undergo in moving from point A here to point B, the displacement is a straight line between point A and point B. The displacement is a state function. It doesn't matter whether we went from A to B along that straight line or we took some other meandering path. The displacement is some value that only depends on where A is and where B is. So it only depends on the state of A, its position, and the state of B, its position. Right? That's the displacement. That's this green dashed line. But if we have the total distance traveled does depend on the path that we take. If we take this path, that's a much longer distance than if we go straight from A to B. Right? So the total distance traveled is a path function. It depends on the path that we take. But the displacement is a state function, right? So this is one example. So now let's look at some other terms that we need to know to looking into thermodynamics. So the universe is everything in existence. Me, you, my board here, my video camera, your computer, your phone, the Earth, stars, all the other galaxies. Everything in the universe is the universe. So the system is that part of the universe that we wish to focus on, the part that we're interested in looking at. And the rest of it is what we call the surroundings. So the rest of the universe, other than the system. So the system plus the surroundings has to give us the whole universe. Because if the system is the stuff that we're looking at and the surroundings are everything else, well then the system plus the surroundings has to be equal to the whole universe. So we have two other terms, exothermic and endothermic. An exothermic process is a process in which energy, in the form of heat usually, flows out of the system. So an exothermic process has heat leaving the system. Remember, the system is that object or set of objects that we're interested in looking at. So if heat is flowing from the system to your hand, then you feel the system as hot. But that doesn't mean that the temperature of the system is high. There's a difference between heat flow and temperature. An object could have a low temperature, but if it's losing energy to the outside, if that system is losing energy, it's still exothermic, but its temperature may be lower than your hand, or the temperature of your hand. So endothermic process, on the other hand, is a process in which energy, in the form of heat usually, is flowing into the system. So the system is gaining energy with an endothermic process, it's losing energy with an exothermic process. So energy is leaving exo means outside, endo means inside. So exothermic means energy is leaving the system, endo it means energy is entering the system. So if heat is flowing from your hand to the system, then you feel the system as cold, right? You're really feeling the energy flow within your hand. You're not feeling the temperature of the system. You're feeling the temperature of your hand. So as your hand gets colder, as your hand loses energy to the system, you feel your hand getting cold. And so you say, oh, that object is cold. But you don't really know what the temperature of that object is, only that energy is leaving your hand and going into that object. So now let's look at a box that initially contains methane and oxygen. So methane is CH4, oxygen is O2, and it undergoes combustion. So we have a chemical reaction, we get carbon dioxide, we get water, and we get energy. So the system that we're interested in is the box. Remember, we're looking at a box that contains some stuff, some methane and oxygen initially, and afterwards it contains some other stuff. The surroundings are everything in the universe except the box, so the outside of the box. We're assuming here that the the edges of the box, the walls of the box are negligibly thin. They don't matter. So the box has some amount of potential and kinetic energy before, and it has some amount of potential and kinetic energy after our combustion process. This difference in energy is the amount of energy that flows out of the box, which is probably done as heat. And we're assuming that the box is, if the box has a constant volume, then it will be heat. So the transition is exothermic, because energy is leaving the system. If our system is not moving, then that means that the potential energy afterwards is less than the potential energy before, because if the system is not moving, the kinetic energy is zero, and that means that this loss in energy can't be from a loss of kinetic energy, it's got to be from a loss of potential energy. So where is that potential energy being lost from? What sort of potential energy is that? That's chemical energy. So remember, the first law of thermodynamics says the total energy in the universe is constant. This is also sometimes called the law of conservation of energy that I talked about earlier. So what this says is that the total amount of energy in the universe is constant. So we can move energy from one place to another. We can move it from inside our system to outside our system. But this means that in moving that energy from inside the system to outside, our system has lost that energy. The surroundings have gained that energy by exactly that same amount. So remember, the system plus surroundings equals the universe. The total amount of energy in the universe before and the total amount of energy in the universe after is exactly the same. We just changed the distribution of where that energy is, and maybe what it looks like, which form it has, kinetic, potential, chemical, things like that. So we're just moving energy around. We don't get to add or subtract any energy from the universe. So internal energy, symbolized with an E, sometimes with a U, capitals in both cases. Internal energy is the energy contained within a system of all types, so potential and kinetic energy. So if we say delta E, delta means a change in, so delta E is the change in energy, change in the internal energy, change in the total amount of energy contained within our system, is equal to Q plus W, where Q is the heat absorbed by the system, and W is the work done on the system by the surroundings. So note that I'm saying on the system. Work, the W here, is work done on the system. If the system is doing work on the surroundings, then the value of W has to be negative. Likewise, Q is the amount of heat absorbed by the system. It's being absorbed from the surroundings. So if the surroundings are gaining energy as heat, that means that the system has to lose energy as heat. That means the value of Q is negative, because the system is not absorbing energy as heat. It's losing energy as heat. It's releasing energy. So if energy is flowing out of the system, then these guys, Q and W, are negative. If energy is flowing into the system as heat or work, then these guys are positive. Now, one of them could be positive and one of them could be negative. The system could be doing work on the surroundings, which would have a negative W, but it could be absorbing heat from the surroundings, and so it could have a positive Q. So they don't have to have the same sign. So this means that with positive values of Q or W, the system's energy is increasing, and with negative values of Q or W, the system's energy is decreasing. And note that the work done by the system on the surroundings is of the opposite sign. So we're talking about the W in that last equation was work done on the system by the surroundings, but work done by the system on the surroundings has the opposite sign of that W. So you have to be careful which convention you're using for signs and which way you're defining Q and W, because not everybody does it the same. So also note that we have no way of directly measuring E, the total internal energy. All we can do is measure changes in energy as we transfer energy from one place in the universe to another. We don't have any idea what the total amount of energy is in the universe, but we can measure movements of energy from one place to another, from one object to another, from one system to another, from one form of energy to another. So thermodynamic quantities always consist of a number, the magnitude, and a sign, so the direction. Just like heat and work, they have to tell us which direction the heat or work is flowing, which direction that energy is moving towards our system or out of our system. So the Zumdahl textbook that I use defines thermodynamic quantities from the point of view of the system. So energy absorbed by the system gives a positive Q or W. Energy released by the system, which means absorbed by the surroundings, gives a negative Q or W. But not all sources define quantities from the point of view of the system. If you define energy from the point of view of the surroundings, then you would have the opposite sign that we use. So I'm always going to use the point of view of the system unless I specify otherwise. So it's important to establish the reference frame of any sources that you're using. If you're using the Zumdahl textbook, you know that all of these energies are being defined from the system's perspective. So positive values means energy is going into the system, negative values means energy is going out of the system. But some other sources that you might find, like on the internet, maybe engineering sources. Engineering sources tend to use a reference frame of the surroundings, whereas chemists tend to use a reference frame of the system, because that's what we're studying. So a very common type of work that's associated with chemical processes is work done by a gas, either through expansion or work done on a gas by compression of that gas. We call this PV work, for pressure volume. So if you look at the combustion of gasoline in a car engine, in the car engine cylinder, when that gasoline combusts, it expands, that pushes the cylinder, right, that pushes the piston inside the cylinder. And this expansion of our system, the system is the cylinder here, this causes work to be done on the surroundings, the rest of the universe, including the car and its passengers. So we have some cylinder, it contains some gas, some combustible gas and oxygen mixture beforehand. We light a spark in there, it combusts, that increases the pressure, it expands the volume inside the cylinder, the piston moves down, that piston moves, turns a shaft, that eventually turns the wheels of the car, that pushes the car along the road, moving the car and its occupants. So we've got some mass being moved. So we've turned some potential energy in the form of chemical energy in the form of those chemical bonds. We've broken some chemical bonds, we've formed some other ones. The formation of those other chemical bonds, that's what's releasing this energy. Right? And that energy that we get out, some of it, most of it goes to heat, but some of it goes to the kinetic energy of moving the car along, right? and its passengers. So moving that mass, that total mass along the road. That's the energy we get out. So suppose we have a gas confined to a cylindrical container with a movable piston. Right? We're simulating what's going on in the car engine here. So we have some gas inside there. We've got our piston, so this part here can move up and down. We've got some pressure being applied to it initially. So we've got some force acting downwards here. That's this force being pushed down on our piston. So this may be from a weight, or it may be from outside air, something like that. Note that outside air exerting a force down, it's really the weight of the air. So our bodies are under approximately 1 atmosphere's worth of pressure. It's about 14 pounds per square inch at sea level on a normal day. That means that for every square inch, you have, square inch is about that big. For every square inch of your body, there are 14 pounds of air stacked up on top of it, going all the way up to the top of the atmosphere. That's where that pressure is coming from. It's that weight of the gas molecules pressing down on your body. So if we have a force acting downwards on our piston, where the piston has some area A, then the pressure P on the piston is equal to F over A, so the force divided by the area. That's how we define pressure. It's a force divided by area. So if our piston expands from our initial state to a final state, so we go from here to there, we've increased the volume of our piston, we've increased the height that our piston is above the bottom of our cylinder here, and the work is equal to force times distance. That force, remember, is the force being opposed. That's the pressure exerted downwards on the piston. The distance moved is that delta H. Delta H is the distance, that change in height. So now we have work is equal to pressure times area, because that gives us the force, right? Pressure equals force over area. Rearrange that to give us force. and that gives us pressure times area, and multiplied by our delta H, our change in height. So now the volume of a cylinder is V is equal to A times H. A is the area of our piston, H is the height of our cylinder. So the volume that our gas occupies is equal to the area of the cylinder, the cross-sectional area, times the height that the piston is above the bottom. Which means that the change in volume of our gas from here to there, that delta V, when our cylinder is expanding, is equal to the area, the cross-sectional area, the area of our piston, times delta H, our change in height of our piston. So this means that now our work is equal to, remember, work is equal to P A delta H. Well, A delta H is delta V. So work is equal to pressure times the change in volume. Now note that that pressure is the pressure being exerted on the piston from the outside. That's this force being exerted downwards. It's not the pressure of the gas inside the piston. That pressure doesn't matter here. Right? It's the pressure, because it's the force being opposed is determining the work. So this above calculation gives us the magnitude of the work done on the system by the surroundings. But remember here, this is the work done on the system by the surroundings. That's what the way that we as chemists are defining work. But is the system gaining or losing energy? If the system is expanding, the system is losing energy. The gas is expanding against the pressure, which means it's losing as it expands. It loses some capacity to expand further. So it has to be losing energy. So the system is doing work on the surroundings. But if the system is doing work on the surroundings, that means that the amount of energy or the amount of work that the surroundings does on the system has to be a negative value. So our work that we have has to be a negative value. So we need to put in a negative sign. So for an expanding gas, delta V is a positive quantity, but W is a negative quantity. Because work isn't being done on the gas, work is being done by the gas on the surroundings. So that means delta V and W have opposite sign, and that means that we have to put this negative sign in there. So now we have W equals minus P delta V. Again, that P, that pressure, is the pressure being exerted on the piston from the outside, not from the inside. So when a gas is compressed, delta V is a negative quantity, but W is a positive quantity. So when we compress the gas, the work done on the system is positive. So W is positive. But now, when we compress the gas, delta V is a negative value. If we go from here back to that, back to there, we lower our volume, which means the change in volume is a negative value. So again, the pressure there is the pressure exerted by the outside on the piston, not the pressure of the gas in the system as it's expanding. So that was the nature of chemical energy.